Hello everyone, how are you? Sorry for slight delay, and today's class is slightly ahead of time uh, because I have another class in my Pariksha Vida batch. Today I am taking a class from a different setup, obviously, as you can see from my out getup, right? So today I am going to discuss the second part of current electricity chapter, and as you know, we have already started the chapter, and if you have missed the part 1, you can go to our channel and check the part 1, right? And but before I start, I just wanted to tell you what we have covered in our part 1 so that you have a clarity. So in this chapter, electric current, Ohm's law, then limitations of Ohm's law, resistance and resistivity, combination of resistances, drift velocity, conductivity and mobility, electrical energy, everything we have discussed in detail, so you can go and check that out. Today's session, we are going to talk about cells, cells in series, cells in parallel, Kirchhoff's laws, and Wheatstone Bridge. And during the class, if you have any doubt, always feel free to ask me in the chat. I will try to address them as much as possible. And if you are a past year student and asking some doubt about counseling, I request you to go and ask Jasmine ma'am. She is more informed about counseling related stuffs. If I am aware, I will definitely try to tell you. Okay. Now let's continue with our session. First, let us discuss about cells. What is a cell? Okay, so far we have hello, Rihan Khan. Hello, next gen. Yes, there is a protest going on. Yes, I know. Yes. So basically, we are basically going to talk about electric cell and um, what is an electric cell basically. So we have already always say that battery. Actually, battery, when you are saying battery is basically a summation of multiple cells. Okay, the unit of battery is cell. So one single, like for example, in biology you may have heard about cells, then tissue, right? So tissue is the larger part, cell is the unit. So here we are talking about one single cell. Okay, basically you can say it's a single battery without anything other than one battery. For example, if you are operating a remote, you require two cells, right? If you are operating some toy cars, you require 5 to 6 cells in that, right? So here we are talking about only single cell. Combination of cell is called a battery. Okay, so that is the difference between a battery and a cell. Now when we talk about battery or cell in ideal world, we say that they have zero resistance of their own, right? uh, but in practicality, the cells also do have a internal resistance. So even if you are saying that cells generally, what we draw so far in our life, whenever we draw a circuit, we draw a cell like this, then we have a resistance like this, and we say okay, the voltage is V, the resistance is R, and we have applied Ohm's law, V is equal to IR, right? That was our life so far. But from now on, the battery will may or may not be a simple ideal battery. It can be a practical battery as well. So what is a practical battery? Practical battery has a unique component which is called the internal resistance of the cell, right? Now what is the meaning of internal resistance? So a cell is basically made up of certain materials, right? For example, a graphite cell is made up of graphite, magnesium oxide, and some other chemical components as well. So those things, they are not perfect. They also have some impurities. They also have some of their properties of their crystals, etc. And based on that, every battery, every cell, every unit of a battery, that is cell, they also have a internal resistance. Okay, that internal resistance prevents the maximum potential of that particular cell. So even if we say that it is a 1.5 volt cell, if you use a multimeter and try to measure it, you might get it a lower value. Okay, if you are using some measuring device which is a multimeter, which can be used to measure the potential, etc. Okay, so that will give you a lower value, slightly lower value. Why you are getting that lower value? Because the cell is not ideal. There are some internal resistance. Because of that, the some potential is actually decreasing. Now there used to be a lot of part associated with it, but those parts are now deleted. Only basic part of the cells are there. So now let us understand what is happening. Suppose we have a cell of EMF E. EMF is basically the voltage of ideal cell, but here because we have an internal resistance, we to differentiate between voltage V and the actual capacity, actual potential of the battery, we denote the electromotive force of the cell to be E, okay, not V. V is denoted by the V is the voltage that you measure across the cell. This is the part of this is the entire cell. Okay, this small r is actually part of the cell. Okay, this is, you cannot cut this r and take it out. This is not possible. This external resistance can be cut and can be removed, but this is part of the cell. This entire thing is called the cell. This is basically your battery. Okay, the way we treat a battery, right? This is the this is your battery. This is the positive side of the battery. This is the negative side of the battery. So in everything is inside the battery casing itself. Okay, you cannot cut this R. This is the simplest representation of the same. Right now, when you connect this cell with the resistance, what will happen? Obviously, some current will flow, and when some current is flowing in the circuit, say I current is being flowing. So what we are interested in? We are interested in measuring this current I and the actual voltage that you are getting from the cell. These are the two things that we are interested in. Okay, so we are interested in the voltage that we are getting and the current that we are receiving when we add a particular resistance R. So these two things we will calculate from this. So how to calculate that? Very simple. Uh, so E is the EMF. What is the total resistance? As you can see, this resistance and this resistance are connected in series. So total equivalent resistance is basically the external resistance plus the internal resistance, right? So R plus small r. So this is the total resistance. Now what is the current? Current will be given by the voltage that you have divided by R plus R. This is the current in the circuit. Now obviously this current is not what we are expecting. We were expecting that we will get a current E by R, right? That was the voltage of the battery, and R is the resistance, but we are not getting it. So we also have to find the effective voltage of the battery as well. How to find the effective voltage of the battery? To find the effective voltage of the battery, we have to take this current and multiply with the external resistance. Okay, this is the voltage drop across the battery. Okay, and this will be E by R plus R into capital R. Okay, in other words, this same voltage can be calculated that, okay, this is the EMF of the cell and some portion of that is being used up by this external resistance, right? So this can be written as E minus I into R, right? So this can be represented by V is equal to E minus I into R. So these are the two same things. You can, some cases we may need to compare them to find some unknown values, right? So this is how you calculate voltage. So these are the both equations are super important to calculate voltages and currents. Okay, in some cases currents will be given, some cases current will not be given. So if current is not given, you may need to use both equations. In some cases currents will be given, so you don't need to use both equation. You can use the simple this equation and calculate the values. Now let's see one problem. This is a problem from KCET. Okay, the year I forgot. I think 2020 or 2022. Okay, so the variation of terminal potential difference with current flowing through a cell is as shown. The EMF and internal resistance of the cell are. So they have given you a voltage versus current graph. They have not mentioned the resistance that is connected. They have only mentioned that the voltage is changing and current is changing, how they are being changed. So EMF and internal resistance that you have to connect. Okay, so and 2 points are shown in the graph. If you see here 3 volt and here 6 ampere. Nothing else is given in this case. And how to solve such cases? We know that EMF of a cell is given by, sorry, voltage across a cell is given by E minus I into R. Okay, E minus I into R. Now, if you can make this current to be 0, if you can make this current to be 0, then V will be equals to E, right? Is there any point in this graph where current is 0? Is there any point in this graph where current is 0? Yes, at this axis, along the y-axis, current is 0. Current is along x-axis, that means along y-axis, when you are going through y-axis, current is 0. So this point is the where current is 0. So this point, current I is 0. So here I is 0. So if I is 0, then this voltage must be equals to the EMF of the cell. So that means from here we can write EMF of the cell is 3 volt. So EMF is calculated. Now we have to calculate the internal resistance. Now how to calculate internal resistance? For that, if we can find a point, where V is equals to 0, if we can find a point where V is equals to 0, then we can say that, okay, V is 0 means E must be equals to I into R. E equals to I into R, right? V 0, our left hand side is 0, so E and E minus IR becomes 0. So E becomes I into R. So internal resistance becomes E upon I, right? Internal resistance becomes E upon I. Now if you see in this setup, where is the point where V is 0? So V is plotted along y-axis, that means along x-axis V is 0. So V is 0 is this point. So this point V is equals to 0. That means at this point E must be equals to IR. Okay. So what is that current? So corresponding current is 6 ampere. So only we need 2 points to solve this problem. So internal resistance R equals to the EMF of the cell divided by current, that is 0.5 ampere. Okay, sorry, 0.5 ohm. Okay, so the correct answer is 3 volt, 0.5 ohm, that is option D, right? And if you want to answer the question with me, feel free, type the answer in the chat itself, right? Now let's move on with cells in series. Now we are slowly moving into some higher parts where we are going to talk about cells in series and cells in parallel. So what is the meaning of cells in series? Cells in series is basically when you are constructing a battery, when you are trying to construct a battery. Okay, so how to construct a battery? For that, we have to connect multiple cells. They can be same, they can be different, but in general, when we say cells in series, we assume that positive, negative, like that, they are connected. You will see that when we are solving the PYQs in our next class, you will see that this is not always the case. Sometimes they might change the pattern. They might say that, okay, in multiple cases, they will say cells are not connected like this. One or two cells are connected in reverse order. So what will be the EMF in that case? So that kind of questions are also coming. But here we are assuming that cells, all of them are connected in proper order, and the entire connection is connected across some external resistance. Okay, external resistance R. Each one of them have EMF epsilon 1 R1, either E1 or epsilon 1, symbols are same. And so on. Okay, so if you try to find the total EMF of such combination, what happens? The equivalent EMF means you can convert this circuit. This is a complex circuit, very long large circuit. We don't want this large circuit. we only want a simplified circuit. In simplified circuit, only one cell is there. Everything else, external component remains same. Okay, so this is our equivalent EMF, this is our equivalent resistance. Both are important in this case. Okay, so in this case, as you can see, the equivalent EMF, they are basically addition of all the EMFs. Okay, and for R equivalent, it is also addition of the all resistances. So in this case, what happens is that EMF as well as the internal resistance both increases. EMF as well as internal resistance both increases when they are connected in series. Okay. Now, what will be the current in the circuit? Current in the circuit will be very simple. Epsilon equivalent divided by R plus R equivalent. Same formula. The same formula that we have done in the previous part. Same formula is applicable to find current in the equivalent case as well. But you have to find the equivalent EMF first before moving on. Now, remember, if n such cell, n identical cell, if n identical cells are connected in series, then the equivalent EMF will be very simply n into epsilon. Okay, n identical cells in series, EMF epsilon, internal resistance R, then epsilon equivalent will be n epsilon, and R equivalent will be n into R. Okay, because you are adding same quantities in n number of times. So 1 plus 1 plus 1 plus 1 plus 1 till n. So it will be n times the EMF value. Okay, so this is a shortcut, sometimes can be handy if you know how to use it. Right? Now let's move on with the question. A car has a fresh storage battery of EMF 12 volt and internal resistance 2 into 10 to the power of minus 2 ohm. If the starter motor draws a current of 80 ampere, then the terminal voltage when the starter is on is. So, EMF is given, internal resistance is given, and they are saying what is the terminal voltage. The quantity V is called terminal voltage. Why it is called terminal voltage? So as I shown you in the initial diagram, so suppose this is your battery. Okay, so when you are measuring the voltage across this end, this is the actual terminal voltage. Inside this there is a EMF, there is a internal resistance as well. So this is E, this is R, this is the terminal voltage. This is the voltage that you are measuring in real, in practical cases. So that's why it is called terminal voltage. Now obviously EMF is given, internal resistance is given, current is given. They are asking you V. We know that V is equal to E minus IR. So just put the value. Don't fall for the language of the question. It is easy question. So current is 80 ampere and internal resistance is 2 into 10 to the power of minus 2. So it will be 12 minus 8 into 0.2, that is just a second, 8 into 2 into 10 to the power of minus 1, or 12 minus 1.6. So it will be 10.4 volt. So it will be 10.4 volt. Easy, easy question. It should not take much time if you are familiar with such questions, and you should be able to solve these questions easily. And if you want to practice more of such questions and follow a proper structured way of preparation, then join our Pariksha Veera batch. The batch is live and it is already, classes are going on. As I am speaking over here, Ankit sir and Jasmine ma'am both are taking their classes in the batch. If you are joining late, you might miss some of the classes. So join today. More details about the batch at the end of this session. Now let's move on with cells in parallel. Now cells in parallel is also very interesting. Here what we are achieving, we are basically connecting the same set of cells. Okay, now instead of connecting them in series, we are connecting them one after another like this. Okay, and like this, and at the end we still have the external resistance connected with this combination. Okay, and we are saying that this is epsilon 1 R1, epsilon 2 R2, epsilon 3 R3, epsilon 4 R4, so far so on. Okay, so this is called parallel combination of resistances. Now in case of parallel combination, what happens is that the EMF of the cell is slightly complicated to calculate, and if you calculate the EMF of the cell, equivalent EMF that is, but the equivalent circuit is same, equivalent circuit will remain same. So no matter what, equivalent circuit will remain same for both cells in series and cells in parallel. So in this case, the equivalent EMF calculation can be calculated as epsilon 1 by R1 plus epsilon 2 by R2, epsilon 3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. So remember, this is the easiest way to remember this formula. And how can you remember? Epsilon 1 by R1, okay, epsilon 2 by R2, epsilon 3 by R3, and in the division you just remove the epsilons and keep everything else as same. So you replace epsilons with 1. So 1 by R1 plus 1 by R2 plus 1 by R3. Here same as parallel combination of resistances, the equivalent resistance is given by 1 by R1 plus 1 by R2 plus 1 by R3, and the epsilon equivalent by R equivalent is given by epsilon 1 by R1 plus epsilon 2 by R2 plus epsilon 3 by R3. Now remember, what is the uses of parallel combination? Parallel combination is used when voltage needs to be constant. Here voltage increase is not very high. Okay, voltage does not increase actually, but voltage fluctuations are very less. Okay, voltage is very much constant. For example, the backup generator generally backup of your say you are using an UPS system to back up your laptop or your computer. Okay, that UPS system have parallel combinations of cells rather than series combination. Series combination is there. Series combination is used to help build up the voltage, and parallel combination reduces the overall resistance of the system. So that's why the voltage remains constant. The resistance does not change too much over time. So whenever you require a voltage, more stable voltage operating process, you require parallel combination. Series combination is required when you require high voltage. For example, the cells of your remote or cells of your remote control car. Okay, so in those cases you require series combination. If you require a constant voltage, you will use parallel combination. Okay, so parallel combination is used when voltage should be constant. Series combination is used when voltage should require to increase the total voltage. Okay, so these are the two separate operation process. Okay, now 10 identical cells. So this is one of the questions that I was talking about. 10 identical cells, each of potential capital E and internal resistance small r, are connected in series to form a closed circuit. An ideal voltmeter connected across 3 cells. It will read. So what is the question? Here we have 10 cells, not 1, not 2, but total of 10 cells. Each of them are connected, but in between um, there is no other resistances. Okay, 10 identical cells of potential E and internal resistance R are connected in series to form a closed loop. Closed loop means they are coming back like this. Okay, positive, negative, positive, negative. So basically they are connected like this to form a closed loop. Okay, total number of cells are 10. Now they are saying that you connect your voltmeter across 3 of these cells. 3 of these cells, what will be the voltage measured by this voltmeter? Okay, so now to solve this very simply, what we have to do, we have to first find the total EMF. Total EMF, because they are connected in series, equivalent EMF will be basically N into E. As I mentioned, if N equal values are connected in series, the equivalent EMF becomes N into E. What is the R equivalent? R equivalent will be N into R, right? Now, why we are doing so? No external resistance is connected. That's why it is important. So, what is the total current in the circuit? Total current in the circuit is epsilon equivalent by R equivalent. There is no other resistance connected in this series. So, that means current will be NE by NR, that is E upon R, right? Now, what will be the voltage? We know that voltage across a battery is given by E minus I into R, right? Here, how many cells we are considering? We are considering three cells. So, it will be 3 into resistance will also be 3R. So, 3R. 3E minus I into 3R. Now, let's see. So, E 3E minus, what is I? I is E upon R into 3R. So, R cancels. Okay. And just a second. Just a second. It will be 3E minus 3R. Where I have made mistake. Okay. So in this case, what is happening here, even though the current is being flowing, okay, when you are only taking 3 E's, okay, not the entire circuit, okay, what is the voltage drop across this? Only voltage drop needs to be considered. The cells can be ignored because you are only using voltmeter. So only the voltage drop needs to be considered. Voltage drop is I into 3R. Voltage drop is I into 3R. You do not need to consider the individual EMFs over here. You can directly apply the Ohm's law, and from Ohm's law, current is given by E upon R, and this is 3R, R cancels, and you get 3. Okay, so the voltage in this case will be 3E. Because there is no external resistance, there will be no voltage drop across the cells. Okay, so you will still get the actual voltage of 3 cells, that is 3E. There you do not need to subtract anything because they are connected in series. There will be no external voltage drop, only internal voltage drop will be there, and it will still be 3E only. Okay, now let's move on with a very important concept, Kirchhoff's laws. There are two Kirchhoff's laws, both of them are super duper important for your KCET exam. Okay, junction rule or Kirchhoff's current law. Junction rule, as per your CBSE textbook, it is called junction rule, but most commonly and across other books, it is called Kirchhoff's current law, or KCL. Okay, at any junction, the sum of currents entering the junction is equal to the sum of currents leaving the junction. What does that mean? What is the meaning of a junction, first of all? So you may have seen in the railways, they say KSR Bangalore junction, okay, or say New Delhi junction, but there will be some stations it is not called a junction. Okay, it is simply called say Srikakulam Road. Okay, so it is not called a junction. What is the difference between a junction railway station and a normal railway station? Let us understand that. This is a real life example. So junction railway station means where multiple lines from multiple directions meet at that point. Okay, for example, if I say Bangalore junction, in Bangalore junction, some trains are coming from Mysore, some trains are coming from in the direction of Mumbai, some trains are coming from in the direction of Chennai. So all of them are meeting at a one particular station, but they are all different lines. So that means they are called junction. Okay, when we say that normal railway station means there is only one line coming from one direction going to other direction. There is no other line coming from separate directions. Okay, only one line is there. It is coming from Bangalore going towards say Mumbai. So this is the only one line. So there is no junction, no meeting happening at that point. That is called single station. Same in electricity also. When multiple current carrying wires meet at a single point, that point is called a junction. Okay, so what is that? How does it look like? We do not need to know the exact circuit, but suppose some current carrying wire is coming from this direction, some current carrying wire is coming from this direction, some current carrying wire is coming from uh, this direction. Okay, when they are all meeting at this point, okay, this point is called a junction. Okay, and some current is going out some other direction, some current is going out in some direction. So these are all incoming, these are all outgoing. Let me use separate color for outgoing, that will give you a better clarity. Okay, let me use this color. Okay, so these are the outgoing points. All the resistances are actually different, they are not same. So this is say R1, R2, or say do not talk about resistance, say current. All the currents are different. This is I1, this is I2, this is I3, this is I4, this is I5, this is I6. None of them are actually equal. Okay, none of them are actually equal. So this is called incoming, this is called outgoing. So like same on your mobile phone, incoming call, outgoing call. These are all incoming, these are all outgoing. So when you are seeing something like this, you might be thinking, sir, how to manage these kind of things? It is very easy, because Kirchhoff said one very important thing is that the incoming current I1 plus I2 plus I3 should be equals to the sum of all the incoming current should be equals to sum of all the outgoing current. So I4 plus I5 plus I6. We will see that in our real examples later on. But you have to remember that whatever current is coming in, the same amount of current, total current, not individual current. Total current coming in is equal to total current going out. So sum of the current entering the junction is equal to sum of the current leaving the junction. So this is our junction. This is our junction. Okay, so Jn in railways refers to junction. So I am writing Jn over here. I do not have that space to write the entire thing. But remember, total current coming into the junction is equals to total current going out of the junction. Okay, and one very important point is that this is a direct consequence of conservation of charge. Okay, conservation of charge principle. This is a very commonly asked question in your PUC MCQs as well as KCET PYQs, that Kirchhoff's current law is a consequence of. So Kirchhoff's current law is consequence of conservation of charge. What does that mean? The total charge of an isolated system must be conserved. So if you consider this point, this is an isolated system. This system is not in contact with anything outside. That means total charge that is coming in per second has to go out as well. In some cases, coming in current may be more, going out current may be less. Okay, number of lines I am saying. Suppose three different currents are coming in, only one current is going out. So in that case, total current that is coming in should be equals to the total current going out, no matter what, because the charge that is flowing through the circuit per second must be conserved. Okay, so the Kirchhoff's current law is conservation of charges. Very important because it is very confusing. Next law we will see that Kirchhoff's voltage law or loop rule. It is talking about a closed loop only, and this is a conservation of energy. I will come to that in a while, but remember that Kirchhoff's current law is conservation of charge. Kirchhoff's voltage law is conservation of energy. So that's why students get confused between these two laws, and they also often mistook that Kirchhoff's current law and voltage law. What is the relation? Just remember, current is basically related with charges. Okay, so that's why it is related with conservation of charges, whereas voltage is related with energy. V is equal to V square into V square by R is energy, or VIT is also energy. So from there you can say that because voltage is related with energy, we will say voltage law is based on conservation of energy. Okay, so that is the major thing. Now, what is the loop rule? So, loop rule is basically algebraic sum of charges of changes in potential around any closed loop involving resistors and cells in the loop is equals to 0. So, let me explain it, and then I will explain it in a simpler way as well. Suppose we have a complicated circuit. Complicated circuit means there are a lot of branches there. Okay, some branches coming from this side, some branches coming from this side. Okay, here we have a cell, some internal resistance. Here also we have a resistance. This is a part of a circuit. This is not the entire circuit. Okay, some current are coming there. But when we can see or find or locate something like this. This is called a closed loop. Okay, no matter how the circuit is, original circuit is constructed, if you can find any such configuration where you can start and end at the same point, that is called a loop. Okay, there can be multiple loops present. There can be smaller loop, bigger loops also. But remember that if you can find a single point loop like this is also a loop, and this in this case also Kirchhoff's law can be applied. Kirchhoff's law is not only applied where you know the entire circuit. You can still apply Kirchhoff's law even if you do not know the entire circuit. Okay, so here suppose EMF of the cell is E, this is R. Okay, one very important point that you have to remember while solving such questions: whatever current is going out of the battery, okay, say I1 here, same amount of current must be coming back to the battery. That is one point number one. For a battery or a cell, whatever current is exiting the battery, the same amount of current has to enter the battery. Now, there may be some resistance, there may not be some resistances, it does not matter, but always remember current outgoing should be equals to current incoming for a battery or a cell. Okay. There can be multiple batteries as well. In multiple batteries, individually, every battery has to obey this. Suppose, let me change this here. Okay, here let me add one cell as well. Okay, so this is say E1, this is say E2. This is R1, this is say R2. So remember, in this case also, whatever current is going out, same amount of current should come in as well. Okay, for a cell or a battery, no matter how much current is going out, the same current has to come in for a cell or a battery. Now this resistance say R1, this resistance say R2. Now suppose current through this branch is say I3, current through this branch say I4. We do not need to know the exact direction of the current. That can be calculated once you are solving the problem. You can assume any direction, but when you apply Kirchhoff's law, there is a rule that how can you add those values. Okay, that is very, very important. When you are adding it, automatically the value will be corrected. If you are getting a positive value after solving, that means the current direction that you have assumed is correct. If you are getting a negative value, that means the current is actually flowing in the opposite direction. Okay, so if you are solving this circuit, for example, okay, you found that I3 is -2. That means I3 is not in this direction, but I3 is actually in this direction, opposite direction. So when you are solving, there will be a question based on circuit. in KCET as well as in your PU. So don't, you have to practice questions on that. Now, whenever you are solving questions on circuit, remember that current can be negative because negative current represents opposite direction only. Okay, negative current represents opposite direction only. Now, how to apply Kirchhoff's law in this particular case? So, first thing is, when you are applying Kirchhoff's law, you have to start in a particular direction. Okay, you have to start in a particular direction. So you have to start, suppose I am taking this point 1, this is point number 2, this is point number 4, this is my point number 4. Okay, now when you are going in the direction of current, when we are going in the direction of current, okay, everything is positive. If we are going in the direction of current, because for example we are going from 1 to 2, we are going in the direction of current. Our chosen direction is from 1 to 2. So that means everything will be positive. So R1 into I3. R1 into I3, this is positive. Multiply voltage drop across any resistor. Voltage drop is V equals to IR, that is Ohm's law, right? Voltage drop is equals to V is equal to IR, that is Ohm's law. So I1, R1, I3 is the voltage drop across this resistor only. Okay, so R1, I3, R1, I3. Now, when you are going across a battery, you have to be careful which direction you are going. So, for a battery, you are going from positive terminal to negative terminal, it will be positive. When you are going from positive terminal to negative terminal, it will be positive. Okay. Sometimes we write it on the right hand side, but for now I am explaining the basic Kirchhoff's law. So in that case, when you are going from positive terminal to negative terminal, when you are going across the path, so you have to close the loop. You are starting at point 1, going to point 2, then point 3, then point 4, then coming back to point 1. This is a closed loop, right? And when you are going from 1 to 2, you are going in the direction of current. So R1, I3 is positive. Now when you are going from 2 to 3, okay, your direction is in this direction, right? Now do ignore the current in the battery. Battery, when you are going from positive to negative, you have to add this as positive. Okay. Now internal resistance, however, you need to consider the direction. So internal resistance, the current that you have chosen is in this direction. Internal resistance current is going opposite to that of your motion. You have to move your pen like this. So when you are moving your pen like this, okay, the current through the internal resistance is in the opposite direction. So that means it will be minus I2 R2. Right. Now next, from 3 to 4. From 3 to 4, again you are going in the opposite direction of the current direction. Current direction is upward, but you are going in this direction. So it will be minus I4 R2. Okay. Now next, from point number 4 till point number 1, you are again going in the direction of current for internal resistance. So it will be positive. So plus I1 R1. Okay. Now for the battery, you are moving from negative terminal to positive terminal. So from negative to positive, it will be negative. When you are completing the loop through the battery, you are moving from negative to positive. So it will be negative E1, and that should be equals to 0. This is the Kirchhoff's law. Now sometimes what we do, we obviously write it like this: R1 I3 minus I2 R2 minus R4 R2 plus I1 R1 equals to E1 minus E2. Sometimes we write the EMFs on the right hand side, okay, for calculations. Okay, you can write the entire equation like this and then rearrange it, or you can just write the resistances and write the EMFs on the other side. But for EMFs writing on the other side, it is slightly different. The rules are slightly different. What is the difference? If you want to remember one rule itself, this is the best rule, because this is directly goes with the Kirchhoff's law. Okay, but if you want to write that voltages on this side, EMF on the other side, I personally prefer this method. That saves some time, that saves one step for me. That's why I write this But for this you have to check the direction of your loop. You are moving in this direction, right? This cell is also sending the current in the direction that you are going. So that's why on the right hand side E1 is positive, whereas from your chosen path this cell is sending the current in the opposite direction. So that's why E2 is minus. So this is the rule when you are writing EMFs on the other side and voltage drop across resistances on the left hand side. So this is the rule. Any one of them you remember, and if you still need any help, you can mention that in the chat below. Right? Now let's move on and solve one more question. Okay. A current of 6 ampere enters one corner P of an equilateral triangle PQR having 3 wires of resistances 2 ohm each and leaves by the corner R. Then the current I1 and I2 are. So here if you see that current I1 and I2 are entering from this point and leaving from here. So from junction, total current that is entering is 6 ampere. It is given in the question itself. 6 ampere current is entering and it is dividing into two parts, I1 and I2, and then it is leaving through this. Okay. Now they have asked you what is the value of I1 and I2. You might be saying, sir, how to solve it? This is a triangle. You have not discussed anything about triangle. But remember that here, if you see, these two resistances are actually connected back to back. So you can draw them without lifting your pen. That means they are in series combination. Okay. So basically this combination, this circuit is very simple. Here we have one incoming current of 6 ampere, which is basically getting divided into two resistors. One is like this, one is like this, and then it is coming out. So you can always redraw the circuit based on the question. So here we have redrawn, this is 2 ohm, this is 2 ohm, this is 2 ohm. All the resistors are 2 ohm. 6 ampere current is coming in and it is getting out. Suppose this is I1, this is I2. Now, Kirchhoff's current law says that I1 plus I2 must be equals to incoming current, that is 6 ampere. Okay, I1 going out, I2 going out, but incoming current is 6 ampere. So from here we can say I1 plus I2 equals to 6. Now, because these two combinations are connected in parallel combination we know that voltage drop across each resistor remains same. Voltage drop across each resistor remains same. So, in this case, voltage drop across these two. So, when you consider these two are being in series, you can simply replace them by a single resistor of 4. Okay, so I1 into 4. Okay, I1 into 4 or 4I1, okay, must be equals to voltage drop across this, that is 2I2. Okay, or you can apply Kirchhoff's law as well. You can take this as a closed loop. Okay, this is a closed loop, so this is the direction positive, this is the direction negative. This is also possible. Okay, I am using voltage, basic principle of voltage, that is Ohm's law. You can apply Kirchhoff's law as well. 2I1 equals to I2. So we have found the relationship between I1 and I2, and I2 is equal to 2I1. So let's go back to this equation and we write I1 plus 2I1 equals to 6, because I2 is equals to 2I1. So 3I1 equals to 6, or I1 equals to 2 ampere. What about I2? I2 will be 6 minus 2, that is 4 ampere. Right? Give me a break. Okay, clear? If you have any doubt, feel free to ask me in the comment section below. Now, another very, very, very important concept, which is Wheatstone Bridge. Okay, so what is Wheatstone Bridge? Wheatstone Bridge is basically a unknown resistance measurement device. Okay, generally, a Wheatstone Bridge has 4 resistors connected like this in the bridge shape. That's why it is called bridge, Wheatstone Bridge. Okay, there is a one bridge over here, another bridge is over here. Okay, and in between there is a galvanometer is connected, which is bridge between two bridges. Okay, so very interesting design. And Wheatstone is the name of the person who first used this concept to measure unknown resistances, and later on it was a revolution at the era of telegram. Okay, when you are sending the telegram, not the telegram app, telegrams used to be sent like messages, like you send SMS nowadays, or Snapchat, or in WhatsApp you send messages. Like that, it was a communicating device from where you can send messages from one place to other. So that was a very difficult task some years back, few years back. Okay, so the telegram was the way to send messages. Okay, now telegram is officially scrapped. Telegraph, uh, the department was called telegraph. Okay, telegram messages are officially scrapped. It is no longer available, but still the technology that he discovered back then revolutionized the entire system. That's why it is very important, and even it is still used in multiple cases in the advanced form, not in the basic form. This is the basic form. In advanced form, there are multiple uses of this in the still in today's date. Okay, now let us understand the concept. So here we have four resistances P, Q, R and S connected like this. Okay, there is a cell connected to the system, and there is a galvanometer connected in between these system. Okay, now we say that our idea is to vary one such resistance so that the system comes into equilibrium. What is the equilibrium means? Or balanced condition or equilibrium condition. Generally, P and Q are known resistors, R is unknown, and S we vary to measure the value of R. That is generally our purpose. Okay, it can the arrangement can be changed, but this is generally the structure. Now, when you adjust the values of R such S such that there is no current passing through the galvanometer. When a current is passing through the galvanometer, it will show a deflection, right or left. Okay. Now, when no current passes through the galvanometer needle points to 0. Okay, it becomes flat. Okay, those who have done experiments in your lab, they know what is a galvanometer. Those who have not, maybe when you are doing the experiments in future months, then you will realize what is a galvanometer. There is an experiment based on galvanometer as well, converting a galvanometer into ammeter, converting galvanometer into voltmeter. Those kind of experiments are there. But anyway, so galvanometer is basically a device which can measure the change in current. Okay, so when there is a current, it will deflect. But when there is a no current, it will always point towards a zero value. So if it is showing a zero value, means the Wheatstone bridge is balanced. Even though there is a battery connected over here, the bridge is balanced, means the voltage, the current passing through the galvanometer is zero. Now, what does that mean? Voltage across the galvanometer 0 means obviously the voltage across these 2 points are same. So, voltage across these 2 points are same. That's why there is no current passing through the galvanometer. And then you can find the condition of the balance. Condition of the balance is very simple. P upon Q equals to R upon S. So, top right, top left by top right equals to bottom right by bottom left, right? So that's how you can tell that top left by top right equals to bottom left by bottom right. Okay, P upon Q equals to R upon S. Okay, some people can write it P upon R is equal to Q upon S. That is also correct. That can also be just cross multiply it. You will get the result, right? So this is the condition of balancing of the Wheatstone bridge. Okay, because it's a KCET class, we are not discussing the derivation here. In maybe in our one shot lecture or in your FA1 session when it is coming up, we will discuss the derivation as well. Now remember that this circuit design or diagram is not unique. There is, you can rearrange the resistances slightly and you can redraw the circuit like this. So remember, this is also a Wheatstone bridge when you draw a circuit like this. Okay, basically what you have done, you have just rotated it. Okay, and by rotating it, the galvanometer is at the center. So that means you have to have a resistance like this and a resistance like this. This is an alternate diagram of Wheatstone bridge. So if you just take this point, if you make this like this and redraw the circuit, it will give you the same Wheatstone bridge. Okay, this is the galvanometer. The central part is the galvanometer. Okay, this is your P, this is your Q, this is your R, this is your S. Okay, so this is the alternate diagram of the same thing. Remember, this also represents a Wheatstone bridge diagram. Now, for balancing condition, obviously you need to check P upon Q equals to R upon S. Now, if the Wheatstone bridge is balanced, what happens next? If the Wheatstone bridge is balanced, obviously, first thing that you can do is that current through the galvanometer is 0. And if the current through anything is 0, basically that is not playing any role in the circuit. That means you can simply remove this galvanometer and redraw the circuit by doing this. Right? You just need to remove the galvanometer. Right? So galvanometer is now no longer there. That means P and Q are in series, R and S are in series. Okay, and their combination is now in parallel. Okay, so balanced Wheatstone bridge means P and Q are in series, R and S are in series, and their combination is in parallel combination. Okay, so this is the balanced condition. There is also an unbalanced condition. Unbalanced condition using Kirchhoff's law is tricky and difficult. Um, we might cover that in our future videos, but not in today's session. But in KCET level, only balanced Wheatstone bridge will be coming. So you don't need to focus on unbalanced Wheatstone bridge. That unbalanced Wheatstone bridge problem, numerical question, did came once in your PUC exam. Okay. Now let's see one question directly from KCET. In the circuit shown, the end A is at potential V naught. Okay, end A is at potential A naught, and NB is grounded. That means potential is 0. Grounded means potential is 0. Okay. The electric current I indicated in the circuit is, so what is the current that is being shown in the circuit? So if you see, the indicated current is indicated at the middle of these two things. So as I mentioned, this entire combination is actually a Wheatstone bridge. Okay, this is a Wheatstone bridge, this is also a Wheatstone bridge. First check that you need to do whether the Wheatstone bridge is in balanced condition or not. So if you see that, so this is, I said P, this is, I said Q. So P upon Q, that is R by R, is what? R by R is 1. What about R upon S? R is R itself and S is also R. So that is also R by R, that is also 1. So definitely this is a balanced Wheatstone bridge. This is a very special case where all the resistances are given same. If all the resistances are given same, definitely it will be a balanced Wheatstone bridge. Now balanced Wheatstone bridge means, what is our first duty? We first remove this central resistances completely. This is not there at all. Okay, basically it's a open portion. So we just need to delete it, erase it. So once we erase this portion, now we will see that these two are in series, these two are in series, and their combination are in parallel combination. So R and R in series means, what is the equivalent resistance? R plus R. In the bottom part also, R and R are in series, so that is also 2R. So both of them are 2R, right? Now what is the parallel combination of these two? Parallel combination of these two, say this is R1, will be 2R into 2R by 2R plus 2R, right? R1 R2 by R1 plus R2. So that means it will be 4R square divided by 4R. 4 cancels, R square R cancels, and you get the equivalent resistance of this entire system is R. Okay, the equivalent resistance of this entire system. Everything was R. There are 5 resistances, but eventually this turns out to be only one single resistance of value R. Right? Now, if you apply the same logic on the second part, again you can obviously remove this galvanometer. Everything is same resistance. So that means you don't need to calculate anything. You just need to first remove the central part. Now for left hand part, everything was R, equivalent resistance was also R. In the second part, everything is 2R. So what we can expect? We can expect the equivalent resistance should also be 2R. No need to do mathematics here. You can do the mathematics, but because we have done it for the first one, we can apply or extend the logic to the second one, saying that everything was R, equivalent resistance was R. Here everything is 2R, so equivalent resistance must be 2R, right? So what is the um, total resistance? Now we have a R and a 2R in series. In between, this is current, this is our 3 volt, and this part is grounded. So this is the ultimate circuit. This complex circuit is now reduced to this one. Okay, this complex circuit is now reduced to this one, right? Now these R and 2R are obviously connected in series, so that means the total resistance will be 3R. R plus 2R is 3R. So now current passing is I, voltage is 3. So what is the current? So we know that V equals to IR. Okay, so here V is 3, I into 3R. 3R is the resistance, right? So I equals to 3 by sorry, it is not 3, it is not given 3, my mistake, it is given V naught. Okay, it is given V naught, sorry. Okay, so V naught equals to I into 3R, or I equals to V naught upon 3R. This is the current in the circuit. Okay, V naught upon 3R is the current in the circuit. Interesting question. Looks difficult, but very easy question. Next, okay, this is the end of today's session. There are 2 homework questions for all of you. Try to solve them and obviously mention the answer in the comment section below. In the given figure, equivalent resistance between A and B will be. So here this is a complex system. If you see, you have to find the equivalent resistance of this system. Obviously, there is a hint. Hint is this. Look at the shape of this. Okay, look at the shape of this. So if you can figure out what is the shape, you know what to do. Okay. Next question. In the following network, potential at O is. So how to do that? Uh, Again, not much is given here. So first, voltage is given here. Resistance is given. Suppose current is passing through this is I1. Suppose this voltage is V0. Okay, what is the current? Apply Ohm's law here. Okay, higher voltage minus lower voltage divided by resistance equals to current. Now suppose here the current is passing is say I2, here the current is passing I3. Apply the same logic. V0 minus 4, here this is the high voltage, this is low voltage, because current overall this is 8 volt, and if you see that these two voltages are low, that means current must flow from this side to this, from left to right, right? So first case 8 minus V0 by 2 equals to I1. Second case V0 minus 4 by 4 equals to I2, and V0 minus 2 by 2 equals to I3. Now apply Kirchhoff's current law. I1 equals to I2 plus I3, and if you apply that, you will be able to solve this equation and find the value of V0. Okay, so this is also super important question. I hope you enjoyed today's session, but before I go, I have to show you something which we are really proud of. That is our NEET results and our JEE Advanced and JEE Mains results. If you see that our topper Sarthak scored rank 10, all India rank 10. He was a student of Vedantu. Then we have Vishrut, Hemant, Murugeshwaran. Here we have Sri Charan, Ayush, Avinash. So they all have bagged a very, very, very excellent result in our NEET batch, right? Next, if you want to check our JEE advanced results, we are very proud to present you our JEE advanced results as well. So you can see that here. Um, All India rank 178, All India rank 252, All India rank 282, All India rank 95, 43, 18. Ridesh got 18 rank, Navneel got rank 22 as well, and we have many others in top 1000. Okay, so they are all 27 ranks in 1000 AIR, and this is JEE Advanced. This is not JEE Mains. This is JEE Advanced, guys. This is the next level of JEE Mains. But JEE Mains also we are not behind as well. As you can see here, we have Ridesh again with IIR rank 35, Prajwal 584, and in between we have 755, 893, 1044, 1281, 1284, 1341, 1484, 1746, 2200 plus JEE Advanced. They have qualified for the exam, right? So this is our JEE Mains results as well. Now at the end, I just wanted to talk a little bit more about our Pariksha Veera batch, those who are interested in joining this batch. So here you will get full PU2 syllabus coverage of KCET as well as your PU2, because obviously PU2 is part of KCET, and you will get 110 hours of lectures per subject, not one subject, and we will teach really slowly everything in detail, in depth as much as possible. We do that in YouTube also, but there are some restrictions in YouTube, but here we will teach you in detail, in depth, and obviously all the doubts that you have will be cleared in the session itself, right? And you will get 20 plus tests per subject as well, 20 plus part and full length tests. So there will be some part test, there will be some full length test. So everything is included inside this uh, batch as well. You will also get teacher notes, assignments, unlimited DPP generator. What else you need? DPP generator daily practice. You want to practice questions? I have solved all the questions. I need more questions to practice. Use our DPP generator. It will generate automatically questions for you based on your level that you select, and it will give you a challenge. You have to solve them and you have to practice more. Okay, and it is delivered in one of the most innovative and leading online platform, online teaching platform, Wave of Vedantu app. Okay, so Wave platform of Vedantu is one of the award-winning platform. So you are going to get the batch through this, and everything priced only for 3499 only. Everything is available only for 3499, and batches are already going on. Classes are already going on. Do join as soon as possible. Don't miss out on this opportunity, right? This is the end of today's session. I hope I really enjoyed the session, you also enjoyed the session, and I'll be back with pyqs and more. Some new things are also coming to your way for your preparation of your fa2. So keep stay tuned with our channel so that you don't miss out, and obviously if you have not yet subscribed, don't forget to subscribe to our channel. I will see you in next lecture. Till then, bye.